Welcome back to the Art of Math. In today's video, we're going to go over the Fibonacci formula, the derivations of it. This is referred to as the Binet formula. So, kind of lied to you guys. I'm not actually going to go over the proofs and the derivations because I think they're actually they're a little too involved for the folks that tend to follow my videos and series. So, instead of doing that, some of you will want to take a look, and I'll provide links in the descriptions. So, I'd much rather, I'm going to just give you guys a high-level overview of the types of proofs and explanations you might find, and if you are interested in any particular one, go and explore it in the description. Alright, so what is the actual Binet formula? It's this. So you might see it in a slightly different form, but the essence is something like this. So if you have phi, which is this 1 plus root 5 over 2, and you plug that in, if you plug this into a calculator, if you want to find the nth Fibonacci number, let's say the 100th Fibonacci number, you would do phi to the 100th power minus this whole thing, the negative 100th power, all over the square root of 5, and out pops your 100th Fibonacci number, which is pretty cool. So how do you get this formula? There's many ways. I've listed a few. So there's recurrence relations, there's this basic method, generating functions, linear algebra, and induction. Alright, so I'm going to very quickly comment. I've written some stuff down here, but you guys, I'm going to pretty much make the decision to kind of skip over this and ignore this because this is getting into the weeds a little too much. Alright, so if you were to go down this route, you might see stuff such as this. And this basically says, just by looking at your Fibonacci recurrence relation, so the nth term is the sum of the previous two terms, then you might take a guess as to what this formula might be. And how might you come up with that? It's not very intuitive unless you've seen a bit more math. So that's why I want to kind of brush it under the rug. So if you've seen a lot of recurrence relations, such as this one where the nth term is twice the previous one, then you could sort of, and maybe you start with a 3, then you would just be doubling the numbers. So just by looking at this, you could tell this is some sort of exponential function. Now, if you guys can't tell that, no problem. That's why I said you pretty much need a little bit of experience either in this field or in differential equations, a more advanced math topic, to have a pretty good understanding to follow this derivation. So I'm not going to go into it. I'm going to have links in the description where you guys can find proof derivations for all of this stuff. So that would be this probably most common method that you'll find of showing this formula, deriving it, which will be using recurrence relations. And that's just, the word recurrence just means this in terms of something else earlier in the series. There's a few unintuitive steps. So there's the first unintuitive step of choosing, guessing the form, and how in the world would you guess it? Through experience. And then there's a second not very intuitive step that you would only kind of know to do from experience in one of these fields, which is once you have a solution which involves this golden ratio, then you would plug it into some sort of linear combination, like some constant times the first r to a power plus some constant times the other. And since we know the first few numbers in the series, we can calibrate these constants and set up a system of equations by plugging stuff in and setting it equal to these first few easy numbers. If you didn't follow that, don't worry. That's my point, is that's the first method. It involves kind of this guess as to what this might be. Alright. Then there's this, what I call basic method. It's not very basic. I'll make a link to it. It's basic in the sense that it does not involve any complicated math. So this method, the recurrence relation method, involves a few steps that if you haven't seen more advanced math, you probably would never know how to do. So the second method, which I'll provide a great link for, has a pretty easy to follow way to get this formula, but the catch there is it's not very intuitive. In other words, if you didn't already know that's the formula, you would not have any idea of like, why are you doing this? So, and this quote basic method will involve just playing around with phi. So we're going to look at phi squared, phi cubed, and we're going to find some patterns and then jump to some conclusions. And from that, we'll pretty nicely get this. But like I said, if you don't already know we're trying to get to this, you might not know what to do with this. So while this uses simpler math, it's a little less intuitive than this first proof. Then you have another approach involving generating functions. I won't even say anything about that. I'll put a link. This is a little more advanced. If you guys are interested, take a look at it. Feel free to put comments, questions, whatever. All right. Then you have linear algebra. You have that approach involving matrices and decomposition of matrices. I'm just throwing around some buzzwords so in case you guys are interested. Don't worry about it. And then finally, the induction approach. This might be the simplest, but it doesn't derive the formula. In other words, if I said, hey, here's a formula, and you wanted to know if this is correct, then you can just prove the correctness. So this just proves whether this is correct. To recap, if this seems like really crazy stuff, just ignore this and continue with the rest of the series. If you're a little more advanced or you really want to get into the weeds and follow the derivations, then check out the links in the description and challenge yourself, and feel free to put comments, questions, anything at all. All right, I will see you guys in the next video where we continue the main theme of the math and nature and art and we get into chaos. So stay tuned for chaos.